So here we've got the setup. We've got the white light coming down, following the line I've drawn on the graph paper. You can see that the beam is spreading out. The white light is not as collimated as the laser light. The laser light stays very compact, parallel edges, whereas this light is diverging slightly, which will introduce uncertainties in our diffraction pattern because there will be this spreading by the time it's reached the screen. I'm now going to put on the diffraction grating to a part that's not cracked, and what you can see on the screen is you can see this central fringe, which is a bit polluted. It looks like there's some sort of redness to it. It's not as pure white as we'd expect. And you can see the first order on either side, and as we would expect, the inner colour is blue. So let's turn the light out so we get a better picture. There is blue going to green, yellow and red, and then there's the destructive interference, and then out here is another further pattern which I don't think you can pick up on the camera. It's very obvious by eye, but the camera is just not sensitive to pick up these fainter light patterns of the second order or the third order. So what we're going to do is I'm going to make marks on the paper in the middle of the blue, the middle of the green and the middle of the red. And I'm going to do this on both sides, and this is the pattern that we will then analyse to come up with our value for the wavelength of light. We would expect the diffraction pattern with the diffraction grating to give us much better results than the calculations with the young double slits, because our diffraction pattern is much sharper and the brighter at the points of constructive interference. So what I will do is I will annotate this piece of graph paper with the key measurements, and then you can work out the wavelengths of the light by averaging and using trig.